Great. So let's start off. Welcome, everybody. So today we take the second part of the lecture regarding multicast. And as I said, please refer to the Cisco white paper that I posted in NMU classes because this is pretty much related. Okay, it covers a lot of the topics that we're gonna have. So guys, as we said, so when we do multicast, so we already talked about what is happening when you have a receiver. Oops. When I have a receiver here, all right? So it means that whenever I need to send a packet and the destination IP address is here, that's the one, and this is a class D. You may remember in V4, okay, in V6, we said that the MAC address should have a prefix with 3333, and we copy how many bits in IPv6, you remember? We copy 24 bits out of the class, out of the multicast IPv6 address. In the case of the IPv4, what we do, we copy part of it, and we only copy 23 of them. All right, so the prefix is different, okay, which is not, it's the procedure is quite similar to IPv6, but the prefixes are different. All right, so we already did talk about it. All right, so this is what is happening. But now let's see when the source is not sitting on the same network with the destination. So we're not on the same subnet, we're not on the same link. So what's going to happen? So it means that locally, what's going to happen with the multicast traffic, the gateway, which should be multicast enabled, should be able to get this traffic and send it in the network, such as it's going to follow all the paths available, such as you can reach receivers. So the question is, okay, what are we going to do here, and how this router knows that actually there's a member on the local network? So there are two things. So here we have the multicast forwarding. So how to forward multicast packets to reach the edges. And once we reach the edge, I have IGMP that runs between the local network, the local router, plus the end host, such as the router knows how many groups have members on the same network. All right? So those are the two things that we're going to see today. So let's talk about IGMP. All right? So IGMP is a protocol, and as you can see from the name, it sits at the same locations as ICMP, which means that this is network layer, all right? But actually, you need to encapsulate those packets in an ICMP packet, in IP packet, all right? So this is just like ICMP, but you add it. The interesting thing is ICMP, you remember ICMP, the protocol, when you have IP encapsulating ICMP, what is the value of the protocol that indicate that this is ICMP? You remember the value? Anybody in the chat? The protocol, yes, OX1, O1, right? But if now we have IGMP, the new value is O2. Makes sense. So what we need to know, so I won't go into the details of the headers and so on because it's more interesting to see how do you process the messages. So first of all, there have been 3 versions of IGMP. The first one was really basic, and there were only 2 messages. A message that we call the membership query, so it have a special type and code and so on, and a report, okay? And then what happened with the version 2, we added 2 new messages, 1, 2 here, which is the leave and the group specific. So we're going to try to understand why did we add those 2 extra messages. And in the version 3, we have this one here, which is okay. But anyway, so let's start with the basic function in V1, let's say. So how does it work here? So as we said, so the gateway of the local network, so this is a local network here, and you have the gateway, all right? And the gateway is what we call multicast enable. What does it mean? It means that this router will start receiving in blue some multicast traffic. And the question that this router should ask is, okay, does it worth sending the traffic on the local network? And to answer this question, I need to know if there's any members. So in order to tell if they're members, the routers, multicast enable, will run IGMP on the local network with the end host. And what it happens, I will send periodically query messages. And periodically means like every 60 to 90 seconds. So by default is like 60, but you can increase it to 90 seconds. And so you send that query message, which is a generic one. And whenever you receive that query, any receiver on the network who belongs to any multicast group will answer by sending a report. Okay? And in that report, normally what you're supposed to do is to answer with one report per multicast group that you have joined. Which means that at the end, the purpose for the router here is not to know for G1 what are the members. Let's say those two guys have joined two multicast group. I'm not interested in knowing how many members. The only thing that I worry about is there at least one member? So as you remember, multicast, we have a scalability issue, and I wouldn't want to start maintaining the complete total list, detailed list of it. Not interested in this because the overhead is too high. So the only thing I want to know is, oh, there's members. G2 also have a member. Who is a member? I don't care because now I will send the traffic in blue, and normally everybody can listen to the traffic. Everybody can listen to the traffic. And the traffic will be filtered based on the Ethernet address. All right. So we have a couple of problems here. The first problem that we need to solve is the fact that on the same local network, we can have like hundreds of thousands of members, which means that if I send one query, I may receive up to thousands of replies, the reports, and the router gonna collapse if everybody answers. What is more, how many answers do I need per multicast group? How much is the list that I need in order to process the messages? How many per multicast group? One is enough, right? One is enough. So the interesting idea that they did here, and this is where you see that this is a concept that we're going to find many times in networks, is the fact that, okay, so either I can try to coordinate the receivers together and say, okay, you go first, I go second, and you put an order, or you say, oh, you should be the one answering, and everybody should, but it requires coordination. And that's really tough when you have a lot of hosts. Or what you can do, you can use randomness. And what do we mean by that? We mean that when I'm going to receive the query, so I'm a receiver, I receive the query. I'm not going to answer right away. What I'm going to do, I'm going to use a timer, a delay timer. And the value of the timer is going to be random. So which means that I wait for the timer. And if the timer expires, I'm going to reply with the report. Okay? Easy? Okay. But look at what is the trick here. The report, I'm going to send it back to the multicast group that I belong to. So I don't reply to the router, but I reply to all the other members. So what does it mean? It means that whoever have a timer still running, and I see a report for somebody else, I say, do I need to send my report since somebody else already fill in? I don't need. So you see, so by multicasting the report and by using a timer, if the timer are truly random, out of all the members, who's going to answer? Normally, only one, the one with the smallest timer. And that's it. So you see, I think it's very elegant here. By using just a random function, I can coordinate thousands of guys and achieve the same result. And if you think about the design, it's so simple. So that's, I think, a pretty good way. So that's interesting looking at this. So as I said, so you basically send it back to the whole group. So it means that the router is supposed to listen to all the multicast traffic. And that is the case. Whenever the router sees some multicast traffic, he's supposed to receive the traffic. So he won't discard it. So it means that any router belongs to any possible multicast group in the world, such as he can receive the traffic. And what is more, you send it with a TTL of 1 because this is just between me and my gateway. I never forward the messages outside of the network. All right, so it works well, but of course you may understand that, okay, so we know how to join. I know how to let the router know that I have joined. First problem, as you may see, is the fact that we said that we need the queries are sent basically every 60 to 90 seconds. So let's say I join a multicast group in my application. I'm supposed to receive a channel on a live IPTV. So if the query have just arrived, I join. I need to wait for a whole 1 minute before I can start joining the next query. And that's too long. So in order to speed up the process, what I may do here is instead of waiting for a query, when I join for the first time, I can send an unsolicited report just to speed up the process. But still the query needs to be periodic. My question now is the following. So the problem that we have now is, let's say I want to leave. How can the router knows that there are no members? So in the V1, we were expecting basically the router to wait until 2 or 3 rounds of queries with no answers before the router can tell that, oh, it means that there's no more members. So I wait for 2 or 3 rounds of queries without any reports to realize that, okay, well, it means that the group is empty, so let's start blocking the traffic for that multicast. So of course, we just realized that this is not maybe so optimal. Why? Because you see that here leaving is implicit. You have no explicit way to indicate that somebody is leaving. So that's the reason with the version 2, we introduce a new message, which is a leave group message. And what it means that whenever I leave the group, I will send a leave message to the router to indicate to the router that actually I don't want to be a member anymore. But does it mean that there's no other members? No, maybe we still have other members. So in parallel, because I need to make sure that there's no other members, I introduce a second message, which is a group-specific query, which means that now when the router receives the leave message, automatically for G, automatically he's supposed to send a query for G. Okay? Such as, if nobody answers, after 1 or 2 rounds, it means that it's empty. Okay, so you may see that it's just improved a little bit, but that was requested. Then what happened? Oh, no, I didn't say. So, and for the version 3, what happened in the version 3 is we added as well. So it means that now when I do a report, what I can specify is I can specify a list of source that I'm going to authorize. So I can say to the router that I want to join this group, but I want to listen to the specific traffic from those specific sources. So I can provide a list of authorized source to the router. And also what I can do, I can also provide a list of non-authorized source. So it means that I can reply to the router to say that I want to join that multicast group, but whenever the traffic is coming from those sources, I'm not interested. So the router may block the traffic not only depending on their members, but also depending on who is the source. All right, so that's what happened in the version 3. All right. So that's it for IGMP. So those are the few design choices that we made. I think it's a pretty interesting protocol. So now what we need is we need to understand, so as I said, we have the internet, we have a source, the source sent to this router. You have routers with so the big question is how can I make sure that the single packet sent by the source will basically be received by everybody else? Given that this is one packet, multiple receivers. So how to do it? So basically, even though in the textbooks, you may read that this is routing, we don't do routing, we do forwarding. So it means that multicast doesn't require to create a table for the purpose of multicast. So obviously, a simple way of doing this is to flout, to say if it's multicast, let me send everywhere. Because if I send to everybody, that includes a member of the multicast. But we know that flouting broadcast at this scale is problematic. So that's the reason we introduced basically three approaches: the source-based trees, the core-based trees, and the source-specific tree. All right. So let's get into the details of those. All right. To understand the source-based tree, oh my God, this one is crazy. Well, what's wrong with the title? Anyway, first I need to explain you the RPF, which is a reverse path forward. So let's see how it works. So one of the problems with the traffic, remember that if I broadcast, if I flout the traffic, I may end up looping the traffic forever in the network. And this is something that I want to avoid. I don't want the traffic from looping. So I need to find a way to block the traffic and prevent the traffic from looping. Now there's something very interesting that they have as an idea. So what they do, let's say I have this router here, and the router is receiving some packet from the source. So what you may expect from the router is all routers are supposed to have a forwarding table coming either from RIP or SPF. And what I'm going to check here is whenever I receive a multicast packet, I will check what is the incoming interface of this packet. And I'm going to check in the table. And I'm going to ask the following question. I'm going to say, okay, I'm receiving this on that interface. Is this the interface that I would use if I need to send traffic back to the source? Is this the shortest path to the source? Yes or no? So I'm comparing this to my table. So to go to the source, am I sending the packet on the same interface on which I just received the multicast traffic? Yes. So then I'm going to flout everywhere. If I'm receiving the traffic on a different interface that is not the one that I have here, what should I do with the traffic? Discard the traffic. And you know something that may seem super like a miracle, but if you do this, you can see that you will never ever have a loop in your network. So by applying that simple condition here, you solve the problems of loops. That's crazy, right? So everybody understand what we check to do the RPF? I check in the table. Am I receiving the traffic on the incoming interface that I use to contact the source? If it's the same interface, I flout. If it's not, I block. Understood? Is that okay? That's very important. Okay, so now let's think about it. So you have to be careful because here, the only thing that we're doing here is we keep sending the packets everywhere. Yes, we don't have loops, but it means that at the end, if I keep doing this, I'm going to reach all the internet. I'm still flouting because did I take into account at any moment what is the multicast group? No, never. I'm just sending blindly while avoiding the loops. So let's keep it in mind. All right. So let's take now the example of the forwarding, which is a source-based tree that relies on the RPF. I'm sorry about this title. It looks so ugly. Oh, I hate it. Anyway. So let's see. Let's say I have this simple here network, and what I represented here before we start multicast, are just indicating what are the shortest path from any router to the source. So in orange, I have the shortest paths as RIP or OSPF have given, because any router is supposed to have this kind of routes. Okay, whatever you do multicast or not, you're supposed to have those routes. So this is the routes that I have. Okay. Any problem with this? That's the shortest path. Whatever. So this is included in the unicast routing tables of the routers. So I'm going to put them in bold. You can see that those are thick lines just to remember what is the shortest path. All right. So let's say now I'm receiving multicast traffic coming from the source. So wait a minute. So let's look at this router first. I'm receiving a multicast packet. What is the question I should ask myself? Did I receive this packet from the shortest path that I used to contact the source? Is it the case? Yes, it is. So what should I do with the packet? Send everywhere else. Let's do it. We did it. The same with this guy. So did I receive the traffic from Did I receive the packet from the shortest path? Yes or no? Did I? Was it the shortest path to the source? Yes or no? Is it? Guys, anybody? Yes, it is. So I sent everywhere. And sorry, I forgot this one too. Anyway, I will explain you later why I didn't do it. But anyway, I sent it here too. So now let's get into this guy here. So this guy received 2 packets. Which one is the shortest path? Is it the left, east, or west? So once again, this guy is receiving from the left and the right. What is the shortest path to the source? Do you remember? Is it left or right? So I know that some people are chatting and I lost the chat. So yeah, welcome back. Okay, thank you. Left. Yeah, that's right. So that is the shortest path. So what happened to the packet coming this way? Too bad. He doesn't make it because the RPF tells us that we shouldn't do it. So what we do, this one, so actually this packet is the one that I sent here. Okay, that's it. So if we keep doing the same, so the tree that we're gonna have goes this way. Okay, so I let you do it. Basically, you need to just realize that anytime I have 2 choices, so we can do it for basically all the packets when we are finished. So let me go here. All right, so I think, oh boy. So wait a minute. So I need to let Keynote do his stuff. So you may see that the same goes here, the same goes here. So you may see that since the shortest path is this way, and the shortest path we said that is this way, okay? So you may see that anything incoming should be basically blocked, all right? All right, so the only way that actually we can do it, this is this way. So it means that at the end, if you look at the tree that we just created, which is here, the traffic will only go on those different links. So did we achieve like a tree with all the members? Yes, we did. So once again, I don't have this one here. I should keep it there. Okay. So as you may see, what's going to happen now, we're still like bothering all the subnets. So the next step that we should take is the following: is can the routers know if they are members locally? And if yes, how can they know if they are local members? How can they know about it? Thanks to IGMP. So it means that by checking the IGMP, I can realize that, wait a minute, I shouldn't send it here. I shouldn't send it here. Oh, no, wait, sorry. I shouldn't send it here because there are no members. Okay? So what's going to happen now, I can also do some kind of improvement, which is the following. So you may see that here, I have no members. So should I still send the traffic on this link since that there's nobody at the end of the branch? Should I do it? Useless, right? So in order to avoid this kind of problem, we introduce a new message. And this is where you see that we have a new kind of message specifically for the use of multicast. And that message gonna install a state. So let's see what is this kind of message. The message is called a prune message. And the prune message that I represent here in red will be sent back to the source. And what's gonna happen at any router that actually I go, I will install a state where I will indicate the interface that I have been pruned. So for multicast, for that source and the multicast G, I will indicate that J have been pruned. I have been pruned. So I maintain a list of the interface where actually there's no members. And those states will be installed as soft states, which means that the question that should always ask is, let's say this guy wants to join. Because of the state, he won't be able to receive the traffic. So thanks to the fact that here those states have been installed with a TTL, it means that at some point they're going to be expiring. The traffic going to flow back on the branch. And so either if I have member, I keep it this way. If there are still no members, what's going to happen? I'm going to send a prune again, install the state with the TTL until the TTL expire. And then because of expiration, the traffic going to go back to the receiver. And if they're members, no prune. If there are still no members, prune message. Everybody understand how it works with the prune? So you need to understand the following as well. Is some students may think that, okay, but professor, if let's say I have a state, SG, and I put the state regarding this interface that is I, they may say that, oh, why should I put a TTL? It could be enough if I send another message that I can call a graphed message. This will remove the state and I'm good. Yeah, but you have to be very careful because the only thing that you know when you send either the graph or the pure message, you send it back to the source, upstream to the source, because you have no way to know who is the router upstream in the tree. You don't know the router. So the only way you can send a message upstream the tree is by using the source. So it means that it's at some point, the shortest path from this router to the source change and goes this way, for instance. It means that can the graph message claim the mess here if the shortest path to the source have changed? You cannot anymore. So you see, so to make sure that actually this is foolproof and whatever changes you have, you can still end up cleaning the states, you still need to use a TTL, even if you have the graph, which actually may speed up the process. So the basic function here is to use a TTL. And on top of this, you may speed up the process by using the graph message. But the graph message alone is not enough, all right? So you see that the soft states are super powerful because you say, I put a state, do I need to worry and clean it later? No, it's gonna clean by itself. So that's what we should use here. So the soft states don't need actually a specific message to clean them. No explicit message, all right? So this is how it works. So given what we just said about the source-based trees, okay? So as you may see, the source-based tree have two phases. First phase, we flout everywhere. Then we clean by putting states thanks to the prune message. We wait for the TTL. At some point, the TTL expire. I flout again. Then I prune again. So you see, so there are multiple cycles where you go through periods where flouting, pruning, flouting, pruning. And those basically are timed because of the TTL. So guys, I have the following question. If you don't have any questions, I have questions. So anybody have a question? No one? Okay. Should I go with my question? No. So we shouldn't ask questions. Questions are forbidden today. Oh, can I? All right. So my question is the following. So we will see by the end of this lecture that actually those approaches that we're talking about, so now we talked about the source-based, right? And we call it the source-based because you see that the tree depends on the root of the tree, which is the source, which means that it's at some point I have a different source, I need to build a different tree. So it means that the state that I have depends on who is the source and the multicast group. Okay, so my question is the following. Do you think that this approach is suitable for large groups with a lot of members or for small groups with very low members? When do you put a state? When do you need to have a state at the routers? Can you tell me? When you don't have members. So the less members mean more states. So if you increase the number of non-members, it means that you need more states and that is not scalable. So it works well here as you have less states. So more members, less states. So that's the logic here. Right? You need to understand that states are bad because we want to make something scalable. And whenever you have a state, the state depends on the number of receivers. So if you need states with less receivers, so the more receivers, the better. So large groups were the good answer. All right? Okay, let's move now to another approach. Because we see that this one that we just talked about doesn't work well for very small groups. So let's see what's going to happen now. What can we do for those small groups? Because we still need small groups. I mean, you know, there's no good multicast. Multicast could be okay. All right. So here, what we're going to do is they're going to define what we call a core or a rendezvous point. And so what it means now, it means that I don't really care about who is the source, but it means that when you want to join a group and you are a receiver, you need to join a specific server that is represented here in blue. So how do I know about the IP of the server? It's available somewhere. Maybe it's hard-coded in the application. Maybe there is a kind of a directory somewhere that tells me that for that multicast group, join that rendezvous point. Anyway, that's not the problem of the protocol. And what's going to happen? Everybody going to send to the RP, to the rendezvous point, a join. Oops. And the join will install a state where I'm going to say that for the group G, I need to go through the interface I. If it's J, for G, I'm going to go through J. If it's K, I'm going to say that to reach a member, I need to go through K. And all the routers going to install those states. Which means that now, when I have a source, what will the source do? She will start sending to the core. And from the core, I'm going to multicast the traffic depending on the states that I installed at the routers. So do I need to prune? No need to prune, because the only branches are the one that leads to receivers. So now, of course, you know what is my question. And I don't think that we should take a polling. So is it good for large groups or small groups? You see that the more members, the more states, because that's what is installed by a join. So this one is much better for small groups. Okay? So you see, so we have one that is good for what we call the dense mode, and this one is good for what we call the sparse mode. All right? Okay. So as you may see here, I tell that it was a tunnel. For what reason? Because you may see that the source will basically send the multicast packet, but in order to reach the core, I'm going to put it inside a tunnel by saying that that goes to the RP. So that goes to the RP. The RP removes this top header and use the inside packet to send it to the members. Okay, so that's the reason here we have a tunnel. Understood the reason? Otherwise, there's no way I can first go through the rendezvous point and then from the rendezvous point to the groups. The other thing that you may see is like whatever is the source, the tree doesn't change because it's rooted rendezvous point. So it means that here you also have less states because in the previous case, the tree depends on the source. In our case, the tree is shared, whatever is the source. Okay, it only depends on the multicast group. Okay, and here leaving is pretty easy. The join messages should be sent periodically. In case there's no join, no more states, no more states, no more branch, no more branch, no more traffic. Okay, so it's pretty straightforward how it works. Okay? Any questions regarding this? So as you may see, one of the problems that we have here is the following, is the fact that, well, the rendezvous point is basically the drawback of this. Why? Because let's say if you have a lot of members in one area, and basically you have the source that is very close to that group. But the rendezvous point still expects you to send it to the RP, and from the RP, downstream again to the receivers. And as you may see, the location of the RP is very critical. And you cannot really have an RP located, whatever the source, to have a good location. So the placement is a big problem. And so that's the reason people start saying that, okay, so, but the RP is a good thing, but instead of having the RP, what should I have? Maybe that should be the source. And so that's the reason we introduced the source-specific tree. And what it means it means that now the join messages, as you may see, doesn't go to the ERP, but goes straight to the source. And so it means that I keep doing exactly the same as previously, but now when I install a state, the state will depend on who is the source. So it means that if you have another source somewhere, you need to have another state for that new source. So for the scalability, you lose the benefit of the scalability because you need as many states as sources. Yeah, but once again, you cannot do omelet without breaking the eggs. So it means that here we optimize the tree, though we are creating some states. So they even introduce a way of basically swapping from one to another. So what they suggest is they say that, let's say that at some point, the source is here, all right? So what they suggest is they say to everybody, okay, keep joining the ERP. And once you start receiving the traffic from the source, what you may do, you may as well at the same time, you may do pings, pings, and you compare the ping to the source. And you compare if the ping is better coming from the source or from the ERP. So if it turned out that actually you are closer to the source, what they propose is to, at some point, to have somebody, still someone can join the ERP, but other receivers, they may go to the source. And so you have a kind of a tree where the source send at the ERP and as well as some receivers. And if at some point the ERP have no members, you replace the ERP since everybody have joined the source. So there's also like a way of basically moving from one tree to another. Okay. So just to conclude, so that's the source specific. So once again, as you may see, so regarding the scalability, all right. So it is measured in terms of states. So that's the most important thing that you can do with multicast, right? Is count number of states. Set the source tree will install the states depending on who is the source and the group, and they are installed with the print message. Okay, so that's the reason this is suitable for the DM, the dense mode. Now, if we move to the core based, so the core based, you see that the state doesn't depend on the source because the tree is rooted as the ERP. They are installed by the join, so which means that here the sparse mode is much better. Okay, less receivers, less states. Okay, and lately we have this third solution here, which is the SSM, the source specific multicast. So here we still have SG. Okay, all right, and so we have many states, but once again, this is a join that's going to do them. So still, this is suitable for the SM. But if you compare those two, so it's just a matter of location. So it depends if the RP or the source have the best location. So if the RP have a good location giving the source, let's keep using the RP. If the RP is kind of not really suitable given the source, let's root the tree at the source. Okay, so that's the takeaway. All right. So probably like a lot of you are asking, what are we doing in the internet nowadays? So you need to know that in the beginning, we have a few protocols that have been standardized, okay? One of them is basically derived from the OSPF, but it takes like a lot of CPU because basically OSPF will calculate the destination, the route, the shortest route to every receivers. So you may see, so that's quite limited. And nowadays, most of the protocols are called the PIM. Okay, why? Because they are independent. And we have the three modes that we just discussed about. So the one that have been standardized and are basically used, okay, are the three that we just discussed about, the GMSM and SSM, giving that they've been placed under the same umbrella, the same naming, which is PIM for Protocol Independent Multicast. Okay. But even though we have those protocols, you need to know that nowadays multicast is not really used for real. Okay. And the reason for this is like we have multiple issues. Okay. And let's see what are those issues. So first of all, a multicast was, before it was integrated to IPv4 and even IPv6. Okay. It was used in what we call the M-bone. So the M-bone was a kind of experimental test bed. And it was just created out of tunnels. So you could run experiments. And at that time, it was primarily used for video conferencing. So we were in the 90s. And so soon enough, multicast was provided in all routers. So it means that nowadays, whenever you have a router, it can do multicast. No problem with this. It has all the protocols. But ISPs don't use it, or they use in a very specific case. So let's try to understand why is it so challenging. First of all, you cannot really have like 5% or 10% or 50% of the routers doing multicast. If you need to do multicast, you need to go all the way. All the routers need to be 100% multicast. Otherwise, if in the middle you have a router that doesn't understand multicast, the packets are discarded. So it's really hard to have like a gradual deployment, or to say that, okay, in the internet, I have few ISPs that do multicast. In the middle, some ISP doesn't want multicast. If somebody don't want to play ball, it's the end. And it happens quite often. Why does it happen often? Because first of all, you understand that since you are duplicating the packets, it's not very safe. It means that if you want to do like DoD attacks, DOS attacks, multicast is your friend, because you can do it, even amplify the attacks, because you can flood the traffic. So most of the time, what do? Most firewalls, they block multicast. Why? Because it's too risky. And what is more, multicast run on top of UDP. UDP, you remember, we don't really like UDP. So it's also another problem. We already said that it's really hard to prevent spammers. So all I need is to know the multicast IP address of a group, and I can send traffic. How can I prevent this from happening? Really hard to do. Then we also have the allocation problem. So let's say at some point I want to do a lecture with Zoom. Who's going to give me the multicast address? Given that the multicast address need to be used in China, France, and the US at the same time, and we all using different ISPs. Who is in charge of allocating the IP address if I need one? And I just need it for 1 hour 15. So you see, so the allocation of addresses is not suitable for multicast applications. So that's another problem. And as I said, firewall. Another problem for the ISP is the billing. You know, usually the ISPs, they charge you per packet. How many packets did I handle for you? So now in the multicast, one packet could be 100 or 1,000 of copies. So what, they're going to charge me like for the 1,000 packets? Impossible. But how can I make sure that those packets belong to the same packet? Which one are duplicated packets? Which one are original packets? I have no way of saying this. But still, I need to charge for the traffic. There's no way of billing here. We don't know how to account for duplicated packets. Problem. So you're going to say, so what? So multicast is a big failure? Well, so nowadays when you use multicast, mainly it's application driven. So it means that when they do multicast, they do it at the application level. So what it means that when you install your application, let's say peer-to-peer live TV, you have your receivers. So you're going to still do multicast, but when you send the traffic to someone, this someone may send it to multiple other receivers. And that guy may send it to other guys like this. Okay? Sorry, this one was not really. So you can still do multicast, but you don't evolve the routers, you just evolve the edges. And this is something that is used by Netflix. So Netflix, what they do usually, they always try to ID the cluster of users. And let's say if you are in the same area, watching the same video, what they will do, they will use your player, such as you can send your traffic to somebody else at the same time who is sitting in the same area. So they are creating clusters of users, such as you send to someone and he send it to somebody else in the same cluster. So Netflix is doing a lot of things. We use it as well in airplanes. So you know when you are in the couch economy class, usually you broadcast one movie, okay, on the given channel. So usually, in order to receive on your screen, the screen on the seats, the video, we use multicast, because otherwise the bandwidth, with 400 uh, players, it would be impossible. You would need too much bandwidth. So they do a lot of broadcast in the airplanes, as well on the TV campuses. When you go on the campus and you have multiple TVs and you stream the same information to all those TVs, this is what is happening. We also can see it, and this is for the French guys, I'm sorry, to Roland Garros. So do you know what is Roland Garros? I'm sorry, it's the same with the US Open. So it means that when you go on the stadium, right, and you have multiple TVs playing live the game, and you're not sitting in the stadium, all those TVs, the video stream is in multicast. So they do a lot of things with this. So we still use the multicast in those cases. And sometimes low, and some ISPs like Free in France and probably China Unicom. I'm not sure if in China, do you receive the TV? Yeah, you receive the TV through your ISP. So some ISPs, they broadcast the live TV using multicast, but that is specific to their customers in their network. Okay, so it doesn't go through multiple ISPs. Multicast is not dead. So it's interesting to see that multicast is available at the routers, but the ISPs don't really know how to handle the traffic, so they're not using it. So it's interesting because there have been a lot of research on this. It's a concept that is proven to be working, and some application cannot work without multicast, but nowadays it is rather limited to some very specific scenarios, specific time of the year, but is not widely used. We've seen that in IPv6 is standardized for some specific local protocols, but nowadays we don't know really how to use it widely at the large scale of the internet. Okay, but it's still out there, and there are still some research about it. Okay, so I think that this is about it. So once again, so multicast provides the only way to basically deliver a lot of data across multiple receivers across the internet. Location independent addresses, which is crazy. An address is supposed to be a locator. In our case, it's not a locator. It just indicate what you're interested in. So you join something because of the data you're going to receive. And that's weird that at the IP level, I worry about what is my interest and not about where am I getting the data from. If you think about the internet right now, you need to select the location and knowing the IP before you can get some content. In that case, I don't care where is it coming from. I just stay put and wait for the data to be pushed to me, which is crazy. The requirement here is, first of all, I need to know who are interested. So I need IGMP. I need to build a tree, because the tree will guarantee that I don't need to duplicate the data at the source. It's going to be duplicated by routers, and I need to find a way to avoid loops. So we already talked about the RPM that does it. Nowadays, it's difficult to deploy the functionalities that are needed, even though it's available at the routers. But setting up multicast at the scale of the internet is super challenging. And nowadays, most of the time, we are using application level through like peer-to-peer application, do a lot of multicast, and they don't really depend on either on the ISP or if the routers are set up with multicast. Okay? So guys, I think that I should keep it short because I don't know what is my ISP doing here. So they're probably updating the network. So I'll be glad to take questions.